So the last video was very qualitative. Let's be a little quantitative. Now there are two conditions that are true at a phase boundary. So when we have a solid and a liquid in equilibrium along this line, or a liquid and a solid gas in equilibrium along this line, or a gas and a solid in equilibrium along this line. The two conditions that have to be true is one, the Gibbs energy of the two phases have to be the same. And we'll talk about this more when we go into thermodynamics. But basically this says the total energy of the solid has to equal the total energy of the gas, which kind of makes sense. If you've got both existing, that means they're equally favorable. So one can't have more energy than the other. So their Gibbs energies have to be equal. The second is that their chemical potential, represented by the Greek letter mu, also have to be equal. Now, chemical potential is a bit of a weird idea, but basically it describes the energy of the phase based on the number of atoms in the phase. So, again, what it's saying is that if their chemical potentials are equal, there's no more reason to have atoms in the solid phase than the gas phase. Fair enough. Now, along each of these phase boundaries, if we use that relationship, what we can find out is that the change in pressure, based on the change in temperature, is equal to the change in entropy divided by the change in volume. Now, this is a really powerful relationship, and this is actually what is defined as the Clausius-Clapeyron equation. Now, we're going to use the Clausius-Clapeyron in a different form where we have an enthalpy of vaporization. And it's going to kind of come from the relationship I'm about to show you, but this is truly Clausius-Clapeyron. We just use a simplified version of it in 152 for predicting vapor pressures. If we look at this delta S is just the change in entropy. So our second phase, entropy of our second phase minus the entropy of our first phase. This V, this volume, is actually divided by moles of gas. And so if we use the substitution that V hat is actually 1 over the density, we end up with this relationship that density 1 minus density 2 times density 1 times density 2 is the other half of this equation. Now this is a bit of a derivation, but the reason I'm showing you this is that if we want to know the slope of this line, which is what this equation represents, we have to know the change in entropy and the changes in density. So if we look at a solid versus a gas, so we'll say phase 2 is the gas and phase 1 is the solid. The entropy of the gas is going to be greater than the entropy of the solid. So this difference here is going to be positive. Now if we look at the density of a gas versus the density of a solid, it's going to be less. So our density of our solid is greater than our density of our gas, and so this is also going to be positive, and this will give us a positive slope. So this is why this line always has to be positive, is that the change in entropy between a gas and a solid is always positive, and the change in the volume is also always positive. If you look at a liquid versus a gas, it's the same idea. The change in entropy between the gas and the liquid is going to be positive. We're always going to have more entropy in the gas relative to the liquid. The density of the gas, density 1, is going to be, density 2 is going to be less than the density of the liquid, density 1. This difference is also going to be positive. So this line here, the change, must also always be positive. So what about this line here, the boundary between the solid and the liquid? Well, again, the entropy is always going to be positive because we have more entropy in a liquid than we do in a solid. The question is, what about the densities? See, density 1 here is going to represent the solid, and density 2 here is going to represent the liquid. Now, if our solid is more dense than our liquid, this is going to be positive, and this is going to tell us that the slope is always up and to the right. If we have something like water, though, the density of ice is less than the density of water, then this number is actually going to be negative. And because we have a negative change in density, what we see with water is that instead of going up, actually the line goes down. And this is going to be true for any material where the density of the liquid is greater than the density of the solid. We'll always have this relationship that actually as you increase pressure, you will create the liquid. Or as you increase pressure at a given temperature, you'll eventually create the liquid. So this is where these lines come from, is looking at this relationship between entropy and molar volume.